Hey, good morning or afternoon, wherever you may be, everybody. Welcome to another edition of Takeo Tuesday. I'm John Barba, and joining me is Rick Mayo. We're both of the Takeo Training Department, and we're going to talk at you today about an issue that's kind of near and dear to our hearts: is piping and pumping of modulating condensing boilers on the residential end. What we're going to be talking about is some of the different piping methods, what we call our primary, secondary, or moose antler piping method, how we might incorporate an indirect. We're going to talk a little bit about hydraulic separators and buffer tanks and when you might use those. And we're going to get into figuring out what water temperature you might need your boiler to make, as well as um, the actual mechanics of sizing the boiler pump, which in my opinion is a lot more important than we've ever really given it credit for. Usually it's, well, what pump did they say? They gave us a 3-speed pump, turn that sucker on to high and let's get the heck out of here. What Rick's going to walk you through is a very specific and very focused step-by-step process to size that pump so it's big enough without being too big. And we're going to talk about what can happen when that boiler pump is actually too big, and that can create an issue. So we'll get into the mechanics and the math of that, and it's actually, I think you find it very interesting. Before we get started, I just want to make sure everybody can hear us okay. On your control panel, you should see, you click on your control panel, you should see a little hand. That shows you how to raise your hand. And I could see, Albert, you've already done it. If you could click on that, that tells me you can hear me. Okay, I see a bunch of people doing that. And there should be a little question mark, and that's how you ask questions. So if you could do that for me, type in a hi, hello, how are you, or some sort of jovial uh, um, message so we know that you can hear us. And what I'm going to say about questions is this: is please ask them throughout the session. Just shoot a question in. That way, we know we haven't bored you to tears, or haven't lost audio or something like that, or lost our connection. That's a good thing to know. But also, geez, if something doesn't make sense or something you need some help with something, please make sure to ask questions and ask questions throughout the session. We don't like to tell our guests here to say, hold your questions till the end, because that's silly. Ask them when you got them. We'll take periodic checks of our little status window here on questions and answer them as we go. Because I just don't like making you wait till the end, because you may have to go somewhere, and we want to get your questions answered as they're fresh and as they come up. So good. It seems like an awful lot of you have figured out that part. So terrific, terrific, terrific. David, you can hear us just fine. Excellent. Kevin, hello. Michael, Eric, Peter, terrific. Glad you could be with us all. So again, this is going to be an exciting and a really fun session, because this is, again, one of, both for Rick and I, one of our favorite favorite topics. So when we talk about piping up modulating condensing boilers, you could look at literally any ModCon boiler manufacturer's instruction manual, which I know we all look at those, right? We all look at the instruction manual before we break into putting that thing together. But you can look into virtually anyone's manual, and you'll see almost, they may be drawn differently, but if you take a good look at them, the piping schematics are pretty much similar. It's primary, secondary piping like we see here, but with a little bit of a twist, okay? With a little bit of a twist. When we do primary, secondary piping with a cast iron boiler, all right, we make a connection. There's the gazouta port up on top and the return port back on the bottom, and we simply connect those with a big hunk of pipe, and we take secondary heat deliveries off of that primary loop. All right, the primary loop is the big pipe, and then we have secondaries, coming off of that with our T's, 6 inches or 4 pipe diameters apart for our different delivery units. That's with a cast iron boiler, and that's done with an eye towards protecting the boiler from low return water temperatures that would create flue gas condensation. We don't want that with a cast iron boiler, but we do want that with a ModCon boiler. We don't want to protect the boiler in any way, shape, or form. We want the lowest possible water temperatures going back to that boiler. The more we abuse that boiler with low return water temperatures, the more it rewards us with efficiency. So our piping arrangement is in no way designed to protect the boiler from low return water temperatures. It's to enhance the low return water temperatures, or encourage low return water temperatures to the boiler.
Sure.
It's also designed to make sure that we have we have adequate flow through what could be a high head loss heat exchanger, whether it's a stainless steel or a cast aluminum heat exchanger. They tend to be higher head loss heat exchangers. So this circulator becomes kind of critical. We want to make sure it's sized big enough without being too big, which again, is something we're going to talk about later on. So what we have here is our primary secondary with a twist. Now, most people will refer to this setup, this piping right here, the boiler piping, as the primary, and then the header, the distribution header, as the secondary. And if you're comfortable with that, that's cool. I always call the big pipe the primary and the smaller pipe the secondary, but that's just me. So as long as you understand what it is, understand your terminology, you're fine. I like to refer to this as the boiler piping or the boiler loop, and then the other loop as the distribution loop. And what we call this thing in general is what we call it moose antler piping. So moose antler for, obvious reasons. You get your moose antlers. There's your moose head and there's your antlers, right? But this piping right here, we would, that's your boiler, or I'm sorry, that's your distribution loop or your heating loop. That's what delivers, it's the delivery loop that delivers the heat to the structure. And then the boiler pipe, the boiler loop is simply the piping that connects that distribution loop to the boiler. So again, whatever you want to call it is whatever you want to call it, but I just want to make sure we identify the terms. A couple of key things right here. Your boiler circulator always pumps into the high head loss heat exchanger, That keeps the pressure up in the boiler, and for very good reason. If we pumped away from that heat exchanger, we might drop the pressure in the heat exchanger. And when that boiler fires up to high temperature to make domestic hot water, it is conceivable that that boiler could flash to steam, and it'll make a hell of a racket. The good news is it won't do it for very long, but the bad news is we've got nothing left. So always pump into that high head loss heat exchanger. That has nothing to do with quote unquote pumping away. We're not pumping away from the boiler. This right here is pumping away, where we're pumping away from the point of no pressure change, that position where the expansion tank connects to the air separator and connects to the system. That we're pumping away. This has absolutely nothing to do with quote unquote pumping away. All right. So I hope that one makes sense. That's your basic piping arrangement. Okay, your basic piping arrangement, where we have, the sizing of your boiler pipe. All right, the sizing of this pipe right here is basically handled in the manual. They'll tell you what size pipe that should be, 3/4 inch, 1 inch. The manual, read the manual. The manual will tell you what that size pipe should be. Sizing of the distribution or the delivery header, that's going to be based on the BTU load of the system. All right, so say we have a 70,000 BTU house. So this pipe here has to deliver 70,000 BTUs. Now, if my delivery is designed to a 20-degree delta T, all right, we remember our universal hydronics formula, which states that GPM equals BTUH divided by the product of delta T times 500. So 70,000 BTUs divided by a delta T of 20 times 500, or 10,000, that will tell us the flow rate through this header should be 7 gallons per minute, and we can size that pipe accordingly. 7 gallons a minute will typically be 1 inch copper. Right, typically be 1 inch copper. There's no harm in oversizing that header. In fact, there is a little bit of a benefit to oversizing the header. A shorter, fatter header gives for better hydraulic separation at that point right there, where the boiler loop connects to the delivery loop. So there is an advantage to oversizing that header. So in this example, it should be at least 1 inch. 1.25 inches is not going to hurt you any. In fact, it could help a little bit. But that's piping up with just a field fabricated header. All right, we'll talk about hydraulic separators in a minute, but I want to make sure this is cool. And I'm going to move on to the same basic piping arrangement, but with an indirect. You'll note when we take the indirect off of the unit here, we're taking it off of the boiler loop, and our supply comes off here at this point on the supply heading into that header. The return comes in after the boiler pump. What happens is when we go into domestic hot water priority, this pump is off. All right, that pump turns off. The boiler fires up to, traditionally, they're different boilers might do this differently, but it'll fire up to whatever its highest temperature is, typically 190. And then this circulator is for my indirect, that is initiated. Again, it's pumping into the high head loss heat exchanger, and our flow obviously goes through the heat exchanger of the indirect, and it bypasses the delivery. When sizing this circulator, you have to account for the flow rate needed for the flow rate needed for the indirect. That could be anywhere from 8 to 10 gallons a minute. So we have to take into account the flow rate needed for the indirect to make our domestic hot water. We have to take into account the head loss of the heat exchanger in the indirect. All right, that has to be added, as well as the head loss through the heat exchanger in the boiler at the flow rate needed for your indirect. So we're going to need to make sure we understand what those numbers are. And again, that's something Rick can go over when we discuss pump sizing for the boiler. So just make sure we understand, we take that into account. There is a very good possibility that this circulator might need to be larger than that circulator. All right, just to take care of the requirements for your indirect. All righty.
Good point.
Go ahead, Rick.
No, good point.
Oh, yep. Now, with a hydraulic separator, there's two schools of thought on hydraulic separators, and that's this thing right here. The first school of thought, and to me the most common school of thought for a hydraulic separator, is that it's a piping convenience. Really, you could look at a hydraulic separator as this piping built for you. All right, it's really nothing more than this piping here, where my boiler loop meets my delivery loop. It's really nothing more than that piping built for you. Now, there are hydraulic separators that might have magnetic dirt separators built in, or air separation medium built in, potentially. But the biggest thing a hydraulic separator is going to do is make sure you have separation between this flow and this flow. It's going to make sure that they're completely separate. So flow through your delivery loop's not going to interfere with flow through your boiler loop. Even when using a hydraulic separator, of course, sizing your boiler pump properly is critically important, as is obviously sizing your delivery pump. When do you use a hydraulic separator versus this type of piping? Well, I look at this type of piping, building your own header. It's going to depend on how many zones you have, the size of the smallest zone, as well as the lowest firing rate of the boiler. If you've got a system where maybe it's a boiler replacement and you've got an old Venturi system or an old two-pipe system where it's one, maybe two zones, all right, and you've got a turn down ratio of 8 to 1 or 7 to 1 or 6 to 1 or whatever it might be. As long as you don't have too many zones, that piping arrangement's just fine, just fine. If you have, if you have a system where you have more zones and maybe the load of the smallest zone is within a few thousand BTUs of the lowest firing rate of your boiler, that hydraulic separator with a little bit of mass to it, with some water content to it, is going to be of a benefit to you to help reduce the likelihood of short cycling. We're going to get into buffer tanks at the end, because buffer tanks come into play when your smallest zone is smaller than the lowest firing rate of your boiler. We want to do everything we can in those instances to prevent short cycling with that boiler. So we'll talk about that at the very end. Last thing I want to talk about before I turn it over to Rick is mixing with a modulating condensing boiler. A lot of folks will look at ModCon boilers and say, great, it's a low temperature boiler. If I make all of my different outputs, so say I got some high temp, some radiant and some radiators, if I make that all one temperature, the boiler reset will be fine and I don't have to mix or anything like that. And there's an attraction to that because it's simpler, right? But let's say you have 3 loads on your system. So you've got basement radiant in the slab. You've got between the floor joist radiant in upper floors, and then you have some radiators or some base. Let's call it some radiators, some panel radiators. Okay, so you've got 3 distinct and separate water temperatures. I'm going to suggest to you that under those circumstances, it might behoove you to mix down the two separate radiant temperatures. So maybe I need 110-degree water in my basement slab, and maybe I need 130-degree water in my between the floor joist radiant. All right, and then I need 150-degree water for my radiators. Well, great. Set up the boiler to deliver 150-degree water. Okay, and let that thing work on its outdoor reset. Then you can add, in a multi-temp, multi-load system, you can add something like this, which is a Taco I valve. It's a motorized mixing valve, and in that green head, there's an outdoor reset control built in. So you put a separate sensor, one sensor out for each one of these heads. All right, so if you get two heads, you'll have three outdoor sensors. You have the boiler outdoor sensor and the two radiant outdoor sensors. All right, but what you'll get is and that'll reset the water temperature for my high temperature radiant, and the separate valve will reset the water temperature for my in the slab radiant. What we're doing here, folks, is we're resetting off of the reset. So think about that for a minute. This boiler absolutely loves low return water temperatures. So when we reset off of the reset, whenever either one of these radiants are running, we're going to be sending even lower water temperatures back to the boiler than the boiler itself would have for the high temperature stuff. So these low water temperatures are going back to the boiler, forcing it to condense more and more. And as it warms up and the water temperatures get lower, man, we really start to kick that thing's butt with low return water temperatures, and it'll reward us with extra efficiency. So don't be afraid to reset off of the reset, okay? This thing's not going to mess with the boiler reset. This is simply resetting. It's resetting from here on out, okay? It's resetting from there on out. It doesn't care what the boiler's doing. It's just taking that water temperature that the boiler's given it and mixing it down to the temperature we need for the radiant, and then it's resetting that. So it's not going to fight with the boiler reset. All it's going to do in this example is going to send the lowest possible water temperatures back to the boiler. So I want to do a little status check. How are we doing out there, gang? Is everything making sense? Okay.
Hey, John.
Yeah.
I answered the question, but go back one slide.
Okay. Oops.
Keep going.
There we go.
Yeah, one fellow was asking about the location. I'm trying to point. One fellow was trying to ask about the location of the air separator and why we weren't pumping away from that. So I answered the question, but go ahead and reemphasize. It's not so much. A lot of people will see the expansion tank hooked to the bottom of the air separator, and they always think, "Oh, pump away." What they're forgetting, no, we're pumping away from the point of no pressure change, which is where the expansion tank meets the system. So in this case, notice how John just circled that. We are pumping away. So he wanted to clarify that because he was focused on that 4900, John. So,
Right. Yeah. This is not the point of no pressure change. This is simply where we put the air separator.
yeah.
What you have here is your point of no pressure change is right here down in the corner. And my system pump is here pumping, pardon my scribbles, away from that point of no pressure change. Very good. I hope that helps. I hope that clears that up for you.
Yep.
A couple of other things. Where are we at? I had wire eye valves with outdoor reset 4 to 6 weeks out.
Good answer that.
Yeah, I couldn't give you a good answer to that other than, we have everything, our suppliers aren't working at full, may not be working at full staffing yet. As we are getting close to being working at full capacity, but still not yet. And our capacity is very focused on circulators at this point. So, that could be a possible reason why they're 4 to 6 week out. It depends on the delivery, Paul. Okay, it depends on what the reps have in stock as well. One of the things about Taco is we don't keep a lot of stock on our shelves. Our reps do that. That's part of our model. So we build to suit the order. If that helps, make sense.
Chris has got one. Do circ pumps go on the supply side or return side? Question mark. I've seen both. Well, I think what you're referring to is side of the boiler. So again, you'll hear me reiterate this later, but just follow what the manufacturer shows you in their book. They'll show you when they want to pump away from their boiler, and they'll show you if they want to pump in. As John elaborated on, there's a lot nowadays. There's a lot of time they specifically want you to pump into the boiler. Not in every case, but again, the manufacturer is the one that has to stand behind everything. So do it as their drawing shows you. And then
Right.
John, you want to do the one from Roger there?
Let's see. Let me
You
pull
see
that
that one?
back up here again.
Do we need the air separator as well as the vent off the hydro separator? That's a good, let us clarify that. Go ahead, John, on a 4900. What does a 4900 give us, John, that little auto air vent doesn't give us?
The 4900, inside the 4900, you've got what we call pull rings, all right, little stainless steel rings that act as uh, they're like a collision medium. The water, as it goes through, the micro bubbles and the mini micro bubbles and the multi mini micro bubbles will glom onto those pull rings. All right. And then as they get more and more of them glom on, they'll get bigger and bigger and bigger. And then they'll go up into the upper portion of the chamber and out the system. What the pull rings do is they create what's called a coalescence effect. And that's what maximizes your removal, the air removal. What the vent on top of the hydraulic separator does, and we're presuming a hydraulic separator, it's just a big cylinder, all right? What happens in there is that the fluid's velocity drops well below 2 feet per second inside that cylinder. And when the water velocity in a system, water velocity drops well below 2 feet per second, okay, dissolved gases have a tendency to come out of solution. It's what happens in a scoop. Okay, same thing happens in a scoop. But when they come out of solution, then we don't want them being pumped into the rest of the system. Then we have that vent there that allows it to come out. So do you need both? I mean, if you really want to control air and eliminate air, then yeah. What's going to happen is anything that's not that doesn't get back through the boiler is going to probably separate in that hydraulic separator, and you want to give it an option to get out of there. So it's kind of like, it's not, well, if I have this, why do I need that? You kind of need both, because not all of the water from the system is necessarily going to go back to the boiler and through the scoop. So you're going to need both in that situation, I think. All righty. Very good. We got some more questions here from George. Is it possible to see a hydraulic separator with two different pipe sizes, boiler system size being on one and system being on the other? They don't
Yeah,
have to be equally sized.
I suppose they could, but the ones I'm used to seeing, George, are the same size, just for the reasons of not having multiple skews. Okay, if you want one where the biggest side is going to set the precedent of the pipe size. So, for instance, you wanted 1.5 inches on the secondary going out to the system, then they're just going to make the other side, and you could bush it down. It absolutely could be less than. A lot of times when we're talking primary secondary, the actual primary portion, those twin T's of the boiler, are one, sometimes maybe even two pipe sizes smaller than the secondary, because we might have a bigger delta T on the boiler, which is what we're going to talk about later, than we do on the system. So the system piping might be bigger than the boiler piping, and a lot of times is. So there's nothing wrong with that based on some of the things we're going to talk about. John's already showed you now. It's going to show you right now, and I'm going to get into later as well.
All right, very good. I want to go over a little example here of what temperature we might need. So let's say, and I think I'm going to have a couple of different numbers here, but what I want to figure out is if I have a specific temperature requirement on my system, all right, going out to my heating system, what temperature does the boiler have to make? What temperature does the boiler have to make? So in this example, I've got 6 gallons a minute at 150 degrees that I need for my heating system. What temperature does the boiler have to make in order to give me that 6 gallons per minute at 150 degree water? Because what I want you to realize is right here, right at this point on that T right there, I have a mix point.
Yep.
I'm mixing a certain amount of hot boiler water with a certain amount of system return water. Because in this example, and in most examples, my flow rate for the system is higher than the boiler's flow rate, the boiler's required flow rate. So when that happens, I'm going to be mixing some hot boiler water with some cooler return water right at that point. So if I needed 150 degree water, let's say for this system, and I set my boiler up to make 150 degree water, Well, I'm mixing a certain amount of 150-degree water in this example with a certain amount of 130-degree water. That's not going to give me 150-degree water, right? I'm behind already, and I'm losing
Yep.
ground quickly. So we got to figure out what water temperature do we need. So there's a math formula for this. I know you're going to love it. Here it is. FA times TA plus FB times TB equals FC times TC. So I changed some numbers a little bit because with the previous example, you could infer. So I just changed my numbers a little bit here. We are smart heating people, right? A lot of I've shown this math formula to guys, and you see that the shoulders just kind of go, oh crap, oh
Yeah.
no, not now. Don't be afraid of math. All the math that's required here is stuff you mastered by 5th and 6th grade. Addition, subtraction, multiplication, and division. We all know how to do that. And if not, we have a phone that can help us do that. The thing here is we have to think systematically, and we just have to know what F and T are. If we're in the heating business, I'm guessing most of you know what F and what T will represent. If you have a good guess, type it in. What does F in this formula, what do F and T represent? It should be fairly easy to figure out because we're dealing with heat, right? Yep, we got flow and we got temp. Perfect. Yeah, you
Yep.
guys know it. It's flow, F is flow, T is temperature. All right, now all we got to do is figure out A, B, and C. What's A, what's B, and what's C? Well, this is a mixing formula, right?
Yep.
This is a mixing formula. We're mixing some of this with some of this to get all of this, right?
Yep.
So we just got to fill in what we know and then do 6th or 7th grade algebra and solve for X. So we got to figure out what we're talking about here. A is the flow in this common piping right here. That's A. We're mixing that. It's the flow and temperature there. B is the flow and the temperature coming out of the boiler. And C is the resulting flow and temperature in my system. All right. So if we think about this, we know 5 of the 6 variables already. We know 5 of the 6 variables. Let's take a look here, okay? Let's take a look. In this example, my flow for the system is 6 gallons per minute at 140. Well, that's C, right? So 6 times 140. Okay. B is the boiler, and that's 4 gallons a minute. This circulator and the boiler requires a flow rate of 4 gallons a minute through that heat exchanger. So I know the flow there is 4 gallons a minute times we don't know. The temperature is what we got to find out. Now we got to figure out the flow and temperature here. So think about this for a minute. If I've got 6 gallons a minute at 140 going out to the system, and I'm operating on a 20-degree delta T in this example, I have to have 6 gallons a minute coming back, don't I? And it's 20 degrees less, so 6 gallons a minute at 120. 6 gallons a minute at 120 enters this T. This pump is on. The boiler needs 4 gallons a minute. So my flow rate through A is going to be 6 gallons minus 4. What am I left with here? That's going to be 2 gallons a minute. And what's the temperature going to be? Well, it has to be 120, right? Does that make sense? So I've just by thinking logically and understanding that what goes into a T has to come out of a T, I've got this thing practically licked. I've got 5 of the 6 variables filled in. So I start out with 2 times 120 equals 4x is going to equal 6 times 140. So 2 times 120 is 240. 4x is 4x. 6 times 140 is 6 times 140 is 840. To solve for X, first thing I got to do is I got to isolate X. So the first thing I got to do is get rid of the 240 over here. So I'm going to, with one of these formulas, what you do to one side, you got to do to the other. So I'm going to subtract 240 from each side. That's going to give me 4X equals 600. To solve for X, I divide both sides by 4. So 4X divided by 4 is X. 600 divided by 4 is 150. So in this example, I'm going to need that boiler to make 150-degree water in order to have 140-degree water, the required 140-degree water in my system. So that's one way to figure this out. Just understand, if I need 140 here and I set the boiler up to make 140, I got nothing. All right. You've got to have at least an idea of what the boiler has to be in order to deliver the temperature that you need. So with that, I'm going to give you guys a break. I'm going to stop talking and hand it over to Rick Mayo to kind of go over some of the mechanics of the piping as well as sizing pumps. So Rick, I'm going to
All
turn this
right.
over to you
Let
right
me
about now.
go
There you
there.
go.
Sharing.
I'm making you the
I'm going to
presenter.
show my screen. Hopefully you can see my screen. Let's go back
There we
into
go.
this and open that up. And I'm going to pull that out of the way and I'm going to shrink that down a little bit. People can see me. Well, that's good. I'm glad you can see me. What we're going to talk about now really focuses on the fact that this is a very important part. See the circulator? I'm showing a bunch of different condensing boilers here. Not that we want to step on anybody's toes or forget anybody. Just understand the circulator, when we're talking about sizing it as a primary or a boiler pump, is very important to the overall efficiency of the system, right? And it does have impact and it can have an effect. So that's what we're going to focus in on that. And hopefully that makes sense. What our focal point's going to be. Now, you've already seen this picture. John showed you this little sketch of a typical moose horn pipe showing a wall hung condensing boiler, circulator pumping into it, and this happens to show three zone pumps. Okay, so what we want to focus on is a couple of points here. This circulator sizing, as mentioned already, and this configuration here of the closely spaced tees. It's a term that we've heard quite a bit. I believe that's a Siegenthaler reference, but we're going to actually kind of expound on that a little more so you feel comfortable with that. The first thing I'm going to say is if we have the capability of letting the boiler manufacturer control our pump, okay, then we want to let that happen for a couple of reasons. But so just understand what this picture is showing you. I have a ModCon boiler. It's depicted as a wall hung unit. This circulator will have line voltage coming from the same boiler, but it also has a control wire that allows the actual boiler manufacturer to control the speed of that circulator based on some information. Now, every boiler manufacturer might be a little bit different, and some of them at this point in time aren't giving you this control wire, and some of them are. So you have to look and see. I'm going to cover both ways of sizing the pump, and the sizing that we're going to talk about applies to both configurations. But we're just acknowledging the fact that nowadays we have these third-party signals, 0 to 10, that our circulators can receive. And then it's like Taco turns the keys over to the boiler manufacturer and says, hey, you run me at whatever speed is appropriate for this current condition. And that's a good thing, okay? So take advantage of it if you can. Here's where the rub's at. Not every boiler manufacturer has that output, and not every circulator manufacturer has the ability to receive that in circulators that are appropriately sized. It's my experience that when a circulator gives you the ability to receive that third-party signal, like 0 to 10 or pulse width modulation or something, normally those circulators are pretty good size, up into the intermediate size, and they tend to be bigger than the boiler actually needs to have on it. So there's kind of a, like I said, it's kind of a rub at that point in time. So just make sure that both those things add up, that the boiler manufacturer has the output and the circulator is the right size and has the ability to receive that signal. And by all means, go ahead and do that. Now let's focus on that same configuration when we don't have that control wire and all we're doing is banging this circulator on and off with a relay through this boiler. Okay, what I'm pointing out is the fixed speed mode of application for that circulator is what you want to be focused on, and that's what we're going to use in our sizing exercise. So just reinforcing this whole primary secondary thing, because again, most of the boiler manufacturers will tend to show you this, not all of them. So let me make this point very clear. You don't always have to pipe primary secondary with a condensing piece of equipment. And you go, what? No, always refer to what the manufacturer shows you in their book. Plenty of these manufacturers show you both. They show it piped in series, which means not primary secondary, or they show it primary secondary, and they'll give you plenty of information to tell you why they're doing what they're doing, and they'll give you the appropriate sizing information, which we're going to review today as well. But generally speaking, if we're going to pipe in primary secondary, what does it give us? And John touched on this already, right? What we want is we never want those two circulators. Let's say it this way: the system circulator and the boiler circulator ever affecting one another. The way that we do that is we achieve hydraulic separation. This is what we're talking about right here. We want those two pumps to never associate with each other. Okay. The other thing is, in the days of when heat exchangers only had very high loss coils in them, so to speak, then what we would do is we would a primary secondary would afford the system circulator to not have to overcome the pressure drop of the boiler's heat exchanger. Therefore, it could be sized more appropriately. Okay, so that just another thing we get out of primary secondary. Again, as I mentioned in a couple slides before, sometimes the boiler manufacturer will give you control of that primary circulator, which we'll say the boiler circulator, and then we can get control of the temperature differential through the full cycle of the boiler. Okay, and again, we'll do some exercises here that'll give you an idea of what I'm talking about as far as what that temperature differential really could and can be. Okay. Then now we'll show you this in better pictures as well, but I'm just another bullet to talk about what primary, secondary can do. Okay, if we don't get the circulator sizing correctly, it could lead to short cycling of the boiler. That's meaning the boiler's coming up to temperature quicker than it does, and it actually shuts off. Okay, remember, we want nice long on times and long off times, and we do that by getting the boiler to come on and stay on and not limit on its high limit. So we're going to get into this. We're going to touch on this bullet quite a bit and show you how to avoid that as best as you can. And then lastly, always refer to the boiler manufacturer's installation instructions. Normally toward the middle or the back of the book, they get lots of drawings, lots of different explanations of why they want done what they do. Always follow that. And we're giving you some general guidelines today that go along with that for the most part. Okay. So let's talk about this whole configuration, primary, secondary, right? And I'm going to show you these simple little rules. Here's A, here's B, and here's C. We're mostly going to focus on A and B, okay? And it is easy as the A, B, Cs. Now, the rules are this. I'm going to give you the rules and I'm going to give you the concepts, okay? Rules are the ones, always tells you to take notes and write things down, right? Concepts, again, are also something we want you to take with you, but it'll all be lodged up here, okay? Uh, you know, who was the great trumpet player? Miles Davis. And they asked him, how do you know all that stuff? And he'd point at his head and he'd say, it's all up here. Anyway, that's where I'm getting at. Okay, primary, secondary rules. The rules are a maximum of 4 pipe diameters. Well, what are you talking about, Rick? We're talking about that A note. Look, I'm talking A here. We're talking A. And anytime you see the word maximum, it doesn't mean to take your tape measure out and measure and cut that piece of pipe that distance. We're saying try to get it closer than that. Okay, people misunderstand when we give words like maximum and minimum, so I always want to point that out. So let's do this together. If we say the maximum is 4 pipe diameters of this secondary header here, okay, and that secondary header was 2-inch, then you'd say, oh, that would be 8 inches, 2, 4, 6, 8, right? So I don't want it to be any more than 8. Again, don't worry about that. understand the concept. What we're trying to do is make sure those two T's are as close together as possible. So you folks that can still see my camera, I want you to hold up one hand like this. That's with one thumbs up. And I'm going to hold the other thumbs up here, and we're going to pretend these are T's. I'm going to take those two T's and I'm going to butt them together as tight as I physically can based on the type of fittings that I'm using, okay? So right now, I've just achieved the concept of getting those T's as close together as possible. I will continue showing you why they want to be close together, but understand that's what we're shooting after when we say a maximum of 4 pipe diameters. Here we go. So the B note is the opposite of that because it says minimum. Okay, so notice the flow directions coming from left to right on my screen. I believe it is on yours as well. So this distance before this first tee wants to be as long as possible at a minimum of 8 pipe diameters. What's 8 times 2? I would need this to be a minimum of 16 inches if this was a 2-inch pipe. Do you see the point there? Okay, once we've already gone through the first tee, the downstream side of the second tee can drop to 4 pipe diameters, half of what it was coming in. I'll show you another picture that'll help drive that home as well. Like I said before, we're going to mainly focus on A and B here and not pay much attention to C. C normally is involved in thermal trapping. And we used to talk about that quite a bit when we were talking about variable speed injection mixing, but it applies to primary, secondary. So I'm not going to just completely poo-poo it. I'm going to say, hey, what we're talking about boiler piping right now, there is some things to do with thermal trapping, but it's not as relevant as it is in days of old. In this picture here, I'm showing you a header that's coming across here, right? And then off of that, I have my T's that are butted together here and my T's that are butted together here, as close as physically possible. What I want you to understand is I'm going to back up this A and this B thing for you, okay? If the flow comes out of this circulator, we have these things in our industry. We talk about flow patterns, and sometimes we misinterpret things from when they actually started. So I'm going to throw some different language at you today. I'm going to say smooth flow coming out of the circulator. What I want to achieve is smooth flow. As soon as I come out of the circulator, because of the mechanical energy that's being added to the fluid by the circulator, I'm in this chaotic pattern, right? I'm every which way. But as it goes by a certain amount of straight pipe, it eventually mellows out and it becomes smooth. And the idea and the concept about the B note here, this B note, is I want nice smooth flow coming into that first tee, right? Once I obtain that, I'm already smooth. This circulator moving fluid can disrupt that a little bit, but not as much. That's why the B note on the downside of these the set of T's is half of what it is on the incoming side. Okay, so it's all about keeping that smooth flow prior to entering the two T's and getting away from this chaotic flow pattern. Some people would say that's turbulent, but that's actually not really turbulent flow. So I want to make sure that you understand what the differences are. If we get down to the brass tacks, you can look up turbulent flow pattern actually exceeds even what we're showing you here as a depiction. So anyway, I hope that helps, and I'm sure there might be some questions out there, but for the sake of time, let's jump into the boiler's heat exchanger. What I'm put as a big note here: know what the pressure drop is of the boiler manufacturer's heat exchanger, and you guys can wink and nod if you know what that means. This is just a generic, this doesn't apply to anybody specifically, but what we're showing you is go to the boiler manufacturer and look at a given gallons per minute flowing through that exchanger. What is the resultant pressure drop? Okay, you have to know that, and that's what these little curves look like. In this case, this one pointed out what you would be at a 30-degree delta T. This shows what you'd be at a 20, etc. Okay, so just know that. What this will do is keep you from oversizing that boiler circulator, which we're going to keep pounding away at you, is a bad thing. So let's go in and focus on these two T's right here, right? I'm going to blow this up And I'm going to have you kind of visualize what's happening at that point right there. Now here it is, kind of a cutaway view of those two T's. The appropriate size boiler circ is going to give you exactly what we want right here, right? We want the coolest water coming back to the boiler and therefore getting the boiler to condense like it's supposed to. Okay. Then the boiler water is heated up, it comes back out, blends at that blending point that John was talking about earlier, and goes out to the system. So this is kind of give you a right hand thumbs up on that one. That's really what we want to happen ideally. Okay. Well, what else is out there? Here's an acceptable flow pattern, right? If I could get all the water to go through the heat exchanger, be heated up, come back out here. Okay. Now everybody goes, yeah, I mean, that seems right to me, but think about this configuration. Notice I have two T's here. And I also have two circulators. I have one up here and one out here, right? What's the you know, the practicality of getting both those circulators to give you exactly the same GPM? Okay, it's very hard to do, right? It's just not very practical. So we say, hey, if you're going to do something like this, you might as well just get rid of that, put two elbows here, and pipe it in series with a single pump, as long as the boiler manufacturer gives you the blessing to do that. Okay. Now let's show you when things get a little rough here. Okay. When we oversize the boiler circulator, and this is haphazard stuff by just doing some things I'll talk about later, okay? I will say this, what you're seeing right here will normally happen on occasion, right? And if you do things right, it won't hurt you that bad, okay? But when you just haphazardly, you know, shoot from the hip and oversize these boiler pumps like has been done for about 15 years now, that this is what I want to focus on. Okay, what we're getting is an undesirable effect. When we take the water I just heated up, and I'm going to send it back across the top of this two sets of this tea right here, and now it's going to blend, and it's actually going to warm up the water returning to the boiler heat exchanger, which is in a condensing boiler is kind of a no-no. We're not. John had mentioned earlier, we're talking about protection, boiler protection. We're not worried about that anymore. We want sustained flue gas condensation, baby. That's what condensing boilers are all about, and that's what we want to try to make happen. Okay. So anyway, I'll give you the thumbs down on that one, and then we'll get into the little details that'll help you do it right in the first place. Okay. Now I'm going to go through this really fast because I got several manufacturers here. Again, I'm not stepping on anybody's toes. I'm not trying to purposely leave anybody out. I'm just saying, look, this is how to go through that boiler's manufacturer's information and make sure you're sizing the pump more correctly. What I'm generally saying is take this circulator out to the extreme that the boiler manufacturer has showed you in writing that you can do. Okay. In this case, I got one from HTP. And I'm going to focus on a 150,000 BTU size all across the board. I think I'm going to show you 4 manufacturers. We're going to go right across the board, same information. Notice they say, hey, you can do a 20. Here's what would it be at a 25. Here's what it would be at a 30. By all means, my push to you is to say, take it out as far as they'll let you. You'll see why as we go here. Okay.
And it's
So
important to
again,
note that that's not the delivery side delta T. That's the boiler delta, the boiler
correct.
side delta T. So
Because we're
let me
sizing
make that
that
distinction.
boiler primary circulator. Good point, John. Yeah, we're talking about the circulator for the boiler. Okay, the system can run at 10-degree delta T. We don't care. We're sizing for the boiler. Good point, John. This is just a blow up of showing you how to read their curves, right? Again, this was done at the factory to make sure what the anticipated pressure drop would be, or the resultant pressure drop would be at a given flow. Now they're showing you this is the curve for the 155, right? And here's what it would be at a tighter delta T, and here's what it would be at even a tighter delta T. And they're just showing you, look, there's not a lot of head loss here in feet, okay? So for the sake of time, let's go to the next one. Here's one from Lochinvar, okay? Let's go with a 155 for consistency and look at what they're showing you, 20, 25, 35. They even give you a maximum flow and a minimum flow. So look at those things as well if it's given to you on the same chart or in another area of the manual. But let's do the same thing with this. I'm just showing you. You go to their chart, you're going to see what the pressure drop would be at these given delta T's, right? Again, on the boiler side of the situation. But any of these numbers that you'll see is relatively small numbers. I mean, with this style of heat exchanger, there's really not a lot of pressure drop. But there's plenty of boilers out there that have higher pressure drop. That's okay, because we're talking about very small circulators anyway. There's not really that much of a benefit. So I'm not picking on people that use a different style heat exchanger. I'm just showing you the information I've given you applies to all of them. Okay, this
So
is how.
could you go back one slide real quick, Rick? I just want to make sure everybody understands that. Here we're talking at a 35-degree delta T. The boiler pump needs to deliver, in this case, 8.5 gallons a minute,
Mhm.
but the head loss through the heat exchanger is only 1.5 feet. Now think about that for a minute. Just think about that for a minute. 8.5 gallons a minute, 1.5 feet ahead. Just
Yeah,
saying.
just saying that we don't make pumps that small, folks.
Right.
So
But I
my
bet you
point.
we could find, I bet you we could give you one that'll do pretty darn close to that.
Absolutely, but especially nowadays that we got this whole variable thing. I think the point John's making is saying, look, even if you have what's known as a higher pressure drop boiler's heat exchanger, that's not a bad thing. You just have to design accordingly. Okay. Again, we're trying not to pick on anybody. Here's one that's a 154. That's close enough to 155. This one comes to us from our friends at NTI as well. 20, 25, 35. You guys see what I'm showing you here? This is all, they're all from different manufacturers, but you see it's kind of the same, right? It's all kind of the same. They'll give you those and then they'll show you the chart and you go through and you figure out which one you want to use. And all I'm pointing out, in my experience, it's best, you're going to get an overall efficiency increase if you stretch that delta T out as far as that manufacturer will allow you. Let's do one more. Here's one comes from Weil McLean, our friends at Weil McLean as well. And on their 155, right? There's a 20, there's a 30, there's a 40. See where this is going. Here's what their chart looks like. I will bring one point up about the way this is done. It's similar, but at the bottom here, I want you to understand they've added into their pressure drop some near boiler piping. So there's additional number there. You can do a comparison and just figure it out. Just don't double dip. When I show you what I mean by double dipping is when I do this, I'm going to show you. And the only reason I'm showing you this, folks, is that just in case you don't have the manual, you don't know, what's going on. It's midnight. It's New Year's Eve. I'm showing you a process here that you could do that's pretty safe. Okay. Take the input of the boiler, right? You're going to derate it one way or another. Remember, these aren't 100% efficient, okay? A lot of this has to do with how we're running it. Are we running it at really big deltas, at really low temperatures? And then and only then are we ever going to see those AFUE listings of 95, etc. Okay, you have to derate for altitude, you have to derate for efficiency, and then you size that circulator based on that. You take the input of the boiler, minus anything for derate on altitude, minus your efficiency, and then that would be your maximum output. And you size the circulator for safety's sake on that. Actually, in some more advanced trainings, I will show you how you can shave that off a little bit as well. So let's do something real quick. If we had that boiler input of 155 and at sea level, I'm showing you a couple examples here. 0.95, right? 0.95 means you're going to say this boiler is operating at its highest efficiency, right? That would be your AFUE of 95. So that gives us a 147,250. That's just taking 5% off, right? If I'm going to run at a 30-degree delta T, remember, I'm going to use whatever number the manufacturer will give me, but if I don't know, and it's a condensing boiler, 30 is pretty safe. You saw that on everybody's information for the most part. You can use 500 if you want to. Hot water is actually 490. Okay. 140-degree water. So I just do this math and it says I need 10 gallons a minute. That's what we're going to use for our exercise, a 10 GPM pump. But what I want you to notice, most people shooting from the hip going to put a 15-gallon a minute pump on there. This is where we start showing you why sharpening your pencil a little bit is going to give you better overall system efficiency. Okay, let's take that same application with a lower, let's say that boiler is going to get hot a lot in a non-condensing mode. So we're going to use 0.86. It's the same math, folks. And for the sake of time, you're going to drop 1 GPM. Okay, now the boiler's a 133.3, not a 147.250, right? So that just drops that 1 GPM. If I was at altitude, again, I'm going to go through this pretty quick for the sake of time. I'm running out. You derate for, like, for Denver, okay, that utility there says, hey, it's about a 16% derate. So I use 0.84. Now that boiler is no longer a 155, it's a 130/200. Then I also get a kick to the shins for the efficiency. See what I'm doing there? I know I'm going fast, but all I do, universal hydronic formula there, I'm going to take the load, divide it by the delta T times the constant, and that tells me I'm going to need 8.4 gallons a minute. Look at that. 8.4 to do a boiler that most people would throw a 15-gallon a minute pump at. You see where this is going? Okay, here's the same D rate, but at lower efficiencies. Lower efficiency, I'm going to slice that up even more. I'm going to be out here at Circulator at 7.6 gallons a minute. Remember, the boiler is 155. So this is where you want to be have an understanding of why that boiler circulator is sizing is important. Okay. Anyway, the pressure drop estimate. This is at midnight. Figure out what the pressure drop of the heat exchanger is. You're going to need some kind of manual, but if you know it's a fire tube style heat exchanger, those are relatively low. Okay, again, I'm showing you at 10 GPM, approximately 2 foot ahead. If I throw some numbers in there for the incidental pipe valves and fittings that hook up to the boiler, again, this is where we were talking about double dipping. Don't double dip here, okay? I'm going to go ahead and just put 2 foot and conservatively 3 foot. So I need a pump that'll do 10 gallons a minute at 5 foot ahead. Okay, I'm going to throw out my best foot forward right now for this offering would be my little 0018E. Remember, with this particular circulator, I have a min-max setting, which means I can go anywhere between the maximum of 44 watts and the minimum of 4 watts. Okay, that's that whole entire shaded area. So our load was 10 gallons a minute. We take it up to 5 feet ahead. We cross, and we're assuming that's the actual system curve, the system resistance of the boiler's heat exchanger and near boiler piping, right? And then I come up with an operating point here. Okay, let's do it. Say you wanted to save a little money, you didn't want all the bells and whistles, and you wanted to do one of our 0015 E3s. Well, just pull up the circulator performance curve, understand what the actual modes of operation are. Now, in this case, we have an automatic mode of constant pressure of 5 foot, an automatic mode of 10 foot, and a maximum speed of 44 watts. Now, you're saying, well, didn't you tell me that I don't use automatic modes here? Don't worry about it. The automatic means it has to have an input. And in a boiler primary circulator configuration, you're never going to get hydraulic changes that the circulator needs to make a decision to speed up or slow down. So simply put, it's just going to come up here to 5 foot ahead. We're right on 5 foot ahead. This will be your operating point for that. So again, just understand in this case, I would take a 0015 E3 and put it at 5 foot ahead constant pressure. It'll run just fine. Don't expect it to move up and down because it won't, but it'll operate similarly to what that 0018 will. So anyway, just remember this, that we're shooting when we do a fixed speed circulator like we're talking about. Okay, now the thing that changes this would be to allowing the boiler manufacturer to control the speed of the circulator. So if you're doing fixed speed circulators and you don't have that external control, I want you to understand this. Here's that same calculation we used at a 30 degree at high efficiency, saying that we needed 10 gallons a minute. What if the load changes to half of that? Here's half a load condition, part load conditions on that system, right? So here's half again. I just took the same calculation, but now I'm using 10 gallons a minute because I know I'm fixed at 10 gallons a minute. What I'm solving for is what's going to be my new delta T. I was at 30 under full load condition, but if I keep 10 gallons a minute, what will be my new delta T? Just remember that. And the point I'm making more than anything is keep that initial gallons per minute as low as possible, and you'll get an overall system efficiency increased as best you can with a fixed speed circulator. Hey, hey,
There you
hey,
go.
back to
Hey,
Barb.
look at that guy. And these are the conditions that you spoke of earlier, Rick, where you will, it's kind of unavoidable. You will get some flow backwards through that set of closely spaced T's. We
You will.
warm up the water as it comes back. That's going to shrink the delta T, and that's just the reality of the situation.
Yes, with a fixed speed circulator.
Right.
Absolutely. Absolutely. But here's another point to bring out since you're emphasizing it. Understand, folks, that when the boiler's running at those low, bench conditions, those lower load requirements, most of these boilers have an outdoor sensor on them, and we're tend to be at a warmer day out, right? So they're already reset back. So when we focus on condensing boilers, it's all about the return temperature to the boiler. Even if I'm mixing a little bit and my temperature's below 130 degrees, guess what? I'm still condensing. Okay,
Right.
so it's not I could be better. Don't get me wrong, it could be better, but it's not the end of the world. Again, that is associated with using a fixed speed circulator at that point. There's some other things like I personally have done in my place where I put a Delta T controlled circulator as my boiler primary because I don't have that third party signal that I can control 0 to 10, etc. So, John, go ahead. I've
Yeah,
gone longer than I should have.
no, no, it's quite all right. It was awesome stuff, Rick. A couple things. One thing about delta T pumping, we've heard people who don't really understand how hydronic systems actually do work say that if you put a delta T pump as your delivery or heating system pump, when it gets warmer, that thing's going to slow down. You'll encourage that backwards flow. That's just not really understanding how systems work. That's going to happen regardless, whether you have a delta T pump, whether you have a delta P pump, or whether you have a fixed speed pump as your system pump, as your delivery heating pump. That's going to happen anyway. It's not going to happen any more with a delta T pump than with a delta P pump because we have a minimum speed on a delta T pump anyway. So
Right.
when you hear something like that, it's coming from someone who doesn't really quite understand how these things interact or system design or system operation. So don't get too flustered about that part of the equation. I want to leave you because we just got a few minutes left. I want to leave you with buffer tanks. Buffer tanks kind of go beyond the hydraulic separator. A buffer tank's just a big honking hydraulic separator. It's this thing right here. It's a big hydraulic separator that adds water content or mass to a mod con to reduce the likelihood of short cycling when we have what we call microzones, when the load of the smallest zone is significantly lower than the lowest firing rate of the boiler. Okay, you pipe it up exactly the same way as a hydraulic separator. It just has more water content. The question always comes in, how do we size one of these things? Here's your piping schematic, and it's the same as a hydraulic separator. But the question is, how do we know what size buffer tank to use? And in my mind, to me, this isn't a pie in the sky thing, or it isn't people are never going to really use it. To me, if you have a system where the smallest zones are smaller than the lowest firing rate of the boiler, to me, a buffer tank isn't a nice thing to do. To me, it's standard equipment. You got to do this to prevent that boiler from short cycling. You short cycle a ModCon boiler to the extent that they can be short cycled, which is pretty remarkable. You not only are you just, the boiler never fires long enough to get efficient, but you're also killing components. You're going to short cycle moving parts into an early grave.
Hey, John.
So there's no upside there. Yeah, go ahead, Rick.
Well, another point is nowadays these boilers are keeping track too. And what do I
Yeah,
mean by that? What do, that they know how many times you've cycled that. It keeps
yeah,
track of every time you fired it. And again, without making the story any longer, anybody can go to these new boilers and find out if that boiler circulator and or the system configuration has been done wrong. So you
yeah.
guys
Right.
remember that.
If
Somebody
you
else
got a
walks
lot
in
of
behind
cycles,
you, that boiler going to tell them exactly what happened to that system.
right, exactly. Let me go through this, and there's a real good anecdotal story about that, which is kind of crazy. Here's how to size it. These are your steps, folks. The first thing you want to find is the minimum boiler firing rate, and then you want to find the BTU load of the smallest zone. So step one is you subtract that BTU load of the smallest zone from the boiler's minimum firing rate.
John, did we lose you? Uh-oh. John is frozen on my end. Send me something, guys, if you folks are seeing the same thing I am. John is frozen. Okay. All right. Yep. Everybody's saying, John, you're frozen. Come back in, buddy. But in the meantime, I'll just go through this with you. Remember that when he's saying the minimum of the boiler, he's not talking about the like when you do 5-to-1 turn down or 10-to-1 turn down, right? I mean, you got to figure out, what that lowest possible firing rate is at full turn down of that particular boiler. Okay. And then you're doing the comparison between the two. What is the minimum load on a design day versus that lowest turn down setting that the boiler can offer as well? So that's what we do with that. Okay. The other thing that we look at is, what is the runtime that the boiler manufacturer wants to be as a minimum. This is what keeps that boiler from banging on and off like we're saying, it leads it to an early grave. So we don't want that to happen. So please look and see. Most manufacturers have kind of settled on 10 minutes as minimum. But guess what? As I talked about earlier, that's absolute minimum. You know what? If you could get it to go 15, that's even better. And we can get it to go 15 by simply changing the size of that buffer tank. We slightly increase it, and probably akin to expansion tanks. You can't oversize a buffer tank for the most part, right? So bigger's better, again, for the sake of the footprint and the dollar figures, all that good stuff. So just remember that. So and I don't have the ability to change John's slides right now. I suppose I could switch around and show you my presentation of this same thing, which is same thing but a little different. But we're already over time. And so I think for the sake of not extending this out any farther and for me not shuffling my old slides in here, we will call it good and open it for last minute questions. I'll try to answer those as best I can, and let's take it from there. Go ahead, send me something. I'm looking at them as they come in. Peter, thank you. Good. Thumbs up, Chris. Appreciate that. We'll try to get to some of these answers, the ones we didn't have time for, but appreciate you sticking with us and being part of Taco Tuesday. So very good. Thanks, Sean. Buffer tanks with built-in heat exchangers. Pat, I'm actually kind of familiar with that because of a company I used to work for, but no names mentioned at this point in time. But they actually had something like that. So all right, very good, Josh. Thank you. Bill and Mike, thank you so much. I'm going to go ahead and call it quits, and I'll get with Barba and find out what happened on his end. It tends to happen, and I don't have his presentation, but join us again. Remember, we're kind of swapping week by week. We do a commercial Taco Tuesday, then we do a residentially focused Taco Tuesday. So we look forward to seeing you. Stay with us, and you folks out there. One last reminder. Wednesday night, tomorrow night, guess what we have? We're starting up the fall session of Taco After Dark. So please look on the media, look around. You can register for that. And that is 7 o'clock Eastern on Wednesday night. And you can do the math on Central Time, Mountain Time, where I'm at, and the West Coast time, and even Alaska time. So you folks that are going to join us from Alaska, it's going to be an early afternoon for you. I'll say so long on behalf of Taco Comfort Solution. Appreciate you all, and we'll see you next time around.